All right, so yesterday we introduced ethers. We talked about preparation of ethers. We saw the industrial method of preparing ethers, and then we saw the alkoxy mercuration method. Today we're going to look at reactions of simple ethers. And they're really, for the most part, non-reactive unless you treat them with really strong acid. So in this case, I'm going to have a generic ether with an R group on one side and an R prime group on the other side. We're going to treat this with a super strong halo acid. So I'm just going to call this HX. And in this case, X has to be equal to bromine or iodine. So this actually won't work with HCl. HCl is not a strong enough acid. And the only basic site on an ether is this oxygen. So we can protonate the oxygen on our ether if we have a strong enough acid. And then we have this halogen floating around, either a bromine or an iodine. However, if we look back at our intermediate that we made, we've essentially created a good leaving group, right? Why is this a good leaving group? Yeah, it's neutral when we kick it off, right? So it's basically like protonating an alcohol and kicking it off, but in this case, we're protonating an ether and kicking it off. So then our halogen that was our leaving group in the first step can attack in as a nucleophile and kick this whole thing off. We end up making an alcohol out of one end, and then the other end is now an alkyl halide, right? So we've split it into two separate pieces in this step. However, normally when we do this, we've got excess acid around. So in this next step, your alcohol can grab the proton from your excess acid. Your other half is still floating around. And just like before, our counter anion, or our conjugate base, is floating around as X minus. And just like before, this can act as a nucleophile and do Sn2 chemistry, kick off that leaving group. And we've essentially cleaved it into two separate pieces, each of which are alkyl halides. And then our byproduct for this reaction is going to be water. Synthetically, this isn't super useful, though. There are a lot easier ways to make alkyl halides. Specifically, we can start with an alcohol and make an alkyl bromide, alkyl chloride, things like that. In fact, we covered a lot of that during our substitution chapter, and we covered some of those reactions during our chapter on alcohols and phenols. Does that make sense? So really, this requires an incredibly strong acid, and you can't have any acid-sensitive functional groups like alkenes around, otherwise you'll run into addition chemistry. So this really only works for simple ethers. So let's even make a note on that. This is one reason that ethers are really good solvents, is they don't tend to be very reactive, which allows us to exploit them as a reaction medium. We don't want them to participate in the reaction. Make sense? All right, there was one other type of ether that I said was the black sheep of the ether family, though. What was that one? Epoxides. Epoxides are a heck of a lot more reactive than these simple ethers, and will do a lot of really interesting chemistry. So let's switch gears and talk about epoxides. And we saw epoxides briefly in our first chapter this term. And we said that if you have an alkene, let me clean this up, you can form an epoxide, which is that three-membered ring. And in this case, just like we saw over here, both of these methyl groups are on the same face, meaning they're cis to one another. That means both of these methyl groups must be cis to one another as well, right? So I'm showing them both as wedges coming off not a wedge and a dash. All right, what reagent do we need to make this? MCPBA is the most common one. What does MCPBA stand for? Not everyone all at once. Man, Armand for the win. There we go. It's going to make everyone feel bad. So if you remember, like Armand, it's metachloro, peroxy, benzoic acid, also known as MCPBA. So that's one method that you can use to make peroxy acids. However, if you started looking through sapling at all for this chapter, you've probably seen another one. This one also works. It's not as common, but you occasionally still see it used. This is peroxy acetic acid. Both of these can be used to accomplish the transformation whereby you convert an alkene to an epoxide, right? The main important part of this is having this peroxide oxygen-oxygen single bond. And I showed you the transition state briefly when we looked at it in chapter 9. All right, there's actually another method, though, where you can make epoxides. And this is through the halohydrin reaction. All right, so let's take a look at this method, and it makes a lot of sense. Let's say we start with that same alkene. This time we treat it with bromine, elemental bromine, and we treat it with water. We're going to get addition of a bromine atom and an alcohol. Will it be syn or anti? Anti. Okay. So in this case, we could have a bromine on either side, but we know that the relative configuration has to be anti to one another. So we could mix or get a mixture of enantiomers out of this. All right, so this is our halohydrin product. The next step of this reaction, I'm going to actually show the bond to this hydrogen, is to treat this with sodium hydroxide. What's the fastest reaction in chemistry? Acid base. This is good. So we steal this proton, give electrons to that oxygen. We'll make an alkoxide anion. The negative charge right there. And then we've got sodium floating around and water as our byproduct. All right, the cool thing with this is we've got bromine, which is a good leaving group. And we've got oxygen, which is a good nucleophile. So what ends up happening is this oxygen can actually collapse down, hit the backside of that carbon, and kick off that bromine in one fell swoop. I should write plus En here too. In fact, let me change this to dashes just to be consistent. Or shoot, sorry, let me clean this up. All right, do we need to worry about making a mixture of enantiomers from this? Yes, no? Why not? It's a meso compound, right? So we made a meso compound. So even though it does have stereocenters on each of the carbons in that three-membered ring, it has an internal plane of symmetry, but we were able to make an epoxide this way. This is called an intramolecular Sn2 reaction. Basically meaning it's going to react with itself and do an Sn2 reaction to form an epoxide. Does that make sense? Yep.
Say we had alcohol on that methyl group by the oxygen, would it still happen, or would we just have red
So you're talking about if we had an alcohol
Methyl, that's directly, yes.
right there?
If that was actually an alcohol group itself right there instead of a methyl group, would we have resonance and would this still work?
So you're asking if there's an alcohol in that highlighted carbon, would there be resonance? Not exactly.
No, I'm saying like the whole methyl group itself is
Even then, there wouldn't be resonance if that were an alcohol. I will say, though, that with this preparation, you're somewhat limited with the types of functional groups you can have, because some functional groups are incompatible with strong bases like sodium hydroxide. So if you've got, let's say, another position that's highly acidic, you wouldn't want to prepare it this way. You would instead want to prepare it through the MCPBA method. Obviously, the MCPBA method or peroxy acetic acid is under acidic conditions, or this one's under basic conditions. So you need to choose the appropriate reaction conditions for any other sensitive functional groups that you have. Yep. All right. So let's do a practice one. Oftentimes predicting the stereochemistry is a little bit tricky. So for this one, we're going to have an alkene like this. We're going to treat it with MCPBA. I want you to determine what product or products you get out from this reaction and include any relevant stereochemistry. I'll get you started too. What I normally like to do is just make my epoxide as is. We know each of those carbons will have a dash and a wedge coming off of them like that. And then the question is, well, what's coming off of each of these positions? And do we need to worry about enantiomers? Who thinks they got this one? A few people? All right. So let's really quickly go back and review, right? Working backwards, what I like to do is focus on the alkyne. And then I'd say, well, on the alkyne, the ethyl group and the methyl group are on the same face of that alkyne, right? Which means they must share either dashes or wedges compared to one another. So let's just say, all right, that methyl group was on the left. I'm going to put the methyl group, in the back on the left. All right, that means if it's coming off a dash, the dash on the right-hand side must be an ethyl group. All right, and then conversely, over here, we have an assumed hydrogen coming off, and then we've got a cyclohexane ring coming off the other side, and those must be on the same face of the epoxide. So will the cyclohexane go on the right or the left? It's got to go on the left, right? And then the hydrogen must come off here. Do we have to worry about a set of enantiomers? That epoxide could face the top or the bottom, right? So in this case, we would absolutely have to worry about a mixture of enantiomers. So we would get both products out of this. In this specific example, we would get a pretty clean mixture of enantiomers, meaning a 50-50 mixture. What do we call that again? Racemic. Would this be optically active? No, they would cancel each other out. This was a big problem in the synthesis community for a while because these are really versatile intermediates, but if you form an epoxide through this method, you're immediately losing 50% of your product, assuming you're trying to make something that's enantiomerically pure. So there was a big hurdle trying to figure out how to make one enantiomer over the other, and in the, I think it was the 70s and 80s, they finally got a method that worked. So I'll show you this one. Enantioselective epoxidation. In fact, the 2001 Nobel Prize was awarded for this chemistry. And in fact, it was awarded to the same chemist that I talked about in the click chemistry lab, Barry Sharpless. So he not only helped pioneer a lot of the major click chemistry, but he was a synthetic chemist that helped master a lot of these enantioselective epoxidation reactions. And what he found was you can do this if you have a very specific alkene. This is called an allylic alcohol. And if you treat this with the correct reagents, you can selectively get one over the other. So for example, you could get this enantiomer exclusively, or at least in like 99% enantiomeric excess. Or using a different set of reagents, you could get this epoxide with really, really high enantiomeric excess. Cool thing with this is you can use relatively simple reagents. You require a peroxide in each case. You also require a titanium catalyst. Oops. Let me clean this up. In both situations, however, the only way we can transfer chirality from one molecule to another is for that molecule to have chirality in and of itself. So what he did was he used a chiral catalyst or a chiral reagent to help transfer chirality. And for the first one, he used diethyl tartartrate. This is a natural salt, something produced in nature. And then for the other one, he used the opposite enantiomer in order to favor the other epoxide. So pretty advanced chemistry. I'll be honest, this isn't a mechanism we're going to cover, and it's not one you'll even see on the ACS exam. I just think it's kind of cool to see this more modern chemistry was able to solve the problem of getting a mixture of enantiomers when you make epoxides. Make sense? All right, there's also other super duper fancy methods where you don't even need allylic alcohols anymore, but this is one of the more famous ones. All right, so now we've got to talk about reactivity of these epoxides and how we can do ring opening reactions. We covered it a little bit in chapter 9, but didn't go into super fine detail. So if we take this alkene, we treat it with MCPBA, we're going to make an epoxide. Do we need to worry about enantiomers for this one? No, again, we've got no stereocenters in there, so we don't even have to worry about this being chiral. All right, and then in chapter 9, I said if you take this epoxide and you treat it with acid and water, the first step will be protonation of the alcohol, or sorry, of the oxygen in your epoxide. And then in the next step, I told you that water would attack one of those carbons, but we really didn't get into which carbon would be attacked because it doesn't ultimately matter that much. All right, but let's think about it, right? If we have a nucleophile I'm just going to draw a generic nucleophile. This nucleophile has a choice. This nucleophile can either attack the more substituted carbon, or it can attack the less substituted carbon. Going back to chapter 9, which one did we observe? The more substituted carbon. All right, so this nucleophile can attack in, slingshot this open. I'm just going to keep this nice and generic now. There's normally a proton transfer process involved. But why does this occur at the more substituted carbon? Who remembers? Hyperconjugation, right? So let's make a note on that. With tertiary carbons, the transition state is stabilized via hyperconjugation. That means that attacking that tertiary carbon is a lot more favorable. All right? So let's kind of highlight this. Unfortunately, this is kind of a half-truth. I lied to you a little bit. There's a lot more nuance to this depending on the nucleophile and whether or not we've got acid around. So let's take a look at some of these weird examples. All right, so let's say we start out with this alkene. Again, we're going to treat it with MCPBA. We're going to make our epoxide. We're going to get a mixture of enantiomers this time. And we're going to treat this with acid. We're going to protonate the alcohol, or sorry, I keep on saying alcohol. We're going to protonate the oxygen on our epoxide just like last time. And now we're going to treat this with a nucleophile. If we look at the carbons in this example, over here, we've got a primary, secondary, or tertiary carbon. Secondary. Then over here, we've got a primary carbon. Up above, in the example that we just saw, I was very clear where I said with tertiary carbons, the transition state is stabilized via hyperconjugation. If we think about secondary carbons, yeah, they do have some hyperconjugation, but not nearly the same as a tertiary carbon. So the nucleophile here, instead of attacking the secondary carbon, because it's not that stabilized, will prefer to attack the primary carbon. Why do you think that is? Sterics, right? It's just more accessible. So then it'll kick up electrons to that oxygen. Let me write plus En down here. And let's make a little note with that. So note, if you do not have a tertiary carbon, then under acidic conditions, your nucleophile will attack the less substituted carbon. So it is kind of weird. In that first example that we saw and talked about in chapter 9, we were trying to explain the regioselectivity due to electronics, where for this example, we're explaining the regioselectivity due to sterics. So there's always this battle in organic chemistry between electronics being the driving force or sterics being the driving force. Sometimes electronics wins out, Sometimes sterics wins out. This is a good example showing the difference between the two. Yep.
So how would you get it attached to the secondary carbon in that situation?
That's a good question. So if you wanted to attack the secondary carbon, you're really somewhat limited using this technique. We'd have to find an alternate synthesis to make that desired alcohol. Yep. All right. Let's take a look though. All of these reactions that we've been seeing, we had a three-membered ring where the atom in the middle, meaning this oxygen here, was protonated or charged, right? Whether or not that's a bromonium ion or the mercurinium ion or a protonated epoxide. In all of the examples we've seen thus far, it's been a positively charged species. Sometimes, though, you can actually open these without that being positively charged. And this occurs under basic conditions. All right, so let's do the same sort of thing. We'll take an alkene, we'll make an epoxide with MCPBA. We'll make our epoxide that's a meso compound. However, in this time, we're going to use a really, really, really strong nucleophile. Meaning it has a negative charge. All right. This one actually is a bit different. In this case, even though we have a tertiary carbon, that nucleophile is kind of behaving like the nucleophiles that we saw in SN2 reactions, right? As a strong nucleophile, would you prefer to attack the less substituted carbon or the more substituted carbon? More substituted. Or sorry, I said more. I should have said less substituted. So in an SN2 reaction, right? Sorry, I completely mimicked somebody that was wrong. I apologize. So that nucleophile, just like with SN2 chemistry, prefers to attack the less substituted carbon because that backside's more available. In this case, electronics doesn't really play a very strong role. I apologize. I wasn't trying to tease you about that. It's been a rough day of lecturing so far. All right. So when you slingshot this open, you've got oxygen with a negative charge. And then what do you think happens in your last step? Protonation. So in step 2, you're going to protonate. However, you should note that this is your second step. Meaning if you number this, this would be step 1 and step 2. And you would protonate to get your desired alcohol. Does that make sense? So let's make a little note here. Actually, I'm going to change this to your nucleophile will attack the less substituted carbon. I don't like to say always. There are, in chemistry, weird examples that will always prove the trend wrong. However, for the most part, under basic conditions, your nucleophile will attack that less substituted carbon. Does that make sense? So this top part is arguably the most tricky thing to remember, right? And that is keeping track of, under acidic conditions, whether or not you've got a tertiary carbon or a non-tertiary carbon. If you have a non-tertiary carbon, you're going to attack the less substituted one. However, if you have a tertiary one, your nucleophile will attack your more substituted carbon. Yeah. Yeah, the weird example is really only true under acidic conditions. So the bottom one was under basic conditions, which is a lot easier to remember because it always goes after the less substituted carbon. All right, in all of these examples though, I've just been writing out NU, meaning some generic nucleophile. the reality is we know of a huge number of nucleophiles that can be used. So what we're going to do is make a mini reaction map just for epoxides. Everybody loves reaction maps. At least Leslie supports me. There we go. So we're going to start with a simple epoxide. And then what we're going to try to do is make a variety of different things. All right, so up here, if we look at the new functional group that we're making a sulfide, right? And to me, this kind of looks like the sulfide is attached to the less substituted side of the alkene. So what does this tell you? Is it under acidic or basic conditions? Basic conditions. So in fact, I'm going to slide things down, and we'll do our reaction map at the top under basic conditions. And what sort of reagent do you think we'll need in order to accomplish this transformation? A strong nucleophile, right? So that sulfur has to have a negative charge. So it could be something like this. However, we can't just buy a bottle of an anion, right? It always has to have a countercation. So quite often what you'll see is sodium listed as a countercation. And you could write it out like that, right? So the sodium has a positive charge, sulfur has a negative charge. That's step one. However, like I said, step two, we need to ensure that that alcohol ends up with a proton. So we need to have a second protonation step. That can be done with any sort of weak acid. However, in our textbook, they normally just show it with water, right? So a two-stepper, we're adding in this thiol portion, and then down here, we're giving up one of the protons from water to that alcohol. Make sense? So we can make a pretty unique functional group that way. All right, the next one's pretty similar. Over here, we're trying to make a nitrile. That's got a carbon-nitrogen triple bond. If you want to draw it out, you can. What reagent would we need to make this? Yeah, sodium cyanide, followed by water. In fact, this would be a very, very dangerous reaction to run under acidic conditions. Does anybody know why? You'd make hydrogen cyanide and poison yourself. You don't want that to happen. So you need to run this one under basic conditions. All right, next one. Let's say we want to make an ether. So if we want to make an ether, right, we can do that. What sort of reagents would we need for this one? We need an alkoxide, right? So it could be sodium methoxide, it could be sodium ethoxide, it could be any one of the alkoxides that we've seen used as nucleophiles. And then in step two, we would include water. All right, there's a couple of other cool ones that we've seen but not really used for this sort of chemistry. Next one's going to be a Grignard reagent. All right, a Grignard reagent by its very nature is a really, really, really strong base. And the carbon's going to act as our nucleophile. So if you use a Grignard reagent, you can actually install a new carbon-carbon bond pretty easily. In fact, let me highlight all of these just so we can keep track of everything. All right, and then the last one under basic conditions is with LAH. Followed by water. Lithium aluminum hydride is also a really strong base, and it's the source of the hydride anion, right? So if we do this, we'll end up installing a hydrogen. Oops. And there we go. So all of these are under basic conditions. Yep. All right. Let's consider acidic conditions, though. Acidic conditions, things are going to change up a bit. So I'm actually going to cut this page kind of in half, like this. And then down below, I'll write under acidic conditions. And we have a handful of different transformations we can do under acidic conditions. The first one is just with dilute acid, right? We actually saw this in chapter 9. We're just going to make an antidiol, right? However, if we were to label our oxygens using isotopic labeling, the oxygen is actually going to get attached onto that more substituted carbon. And why is that? Yeah, it's a tertiary carbon. So we could, if we wanted to, explore this using some sort of isotopic labeling technique. All right. The next method is a little bit different. You need to have some sort of external source of acid, and then you would need some sort of thiol reagent. And just like with the other one, the thiol is going to attach to your more substituted carbon. All right, you can do this with alcohols as well, where you can use some sort of external acid and an alcohol. This could be methanol, ethanol, you name it. And you can make an ether this way. All right, and then the last one's pretty straightforward. This is one where we just use a halo acid. And this time we can actually install a halogen and essentially make something that looks a lot like the product from a halohydrogen reaction. However, how does it differ from the halohydrogen reaction? What's that? Yeah, exactly. For these reagents, the alcohol is on the less substituted carbon versus the halohydrogen reaction. The alcohol ends up on the more substituted carbon. So you can oftentimes play some of these games to change which carbon things are attached onto. It's kind of clever. All right, I did want to really briefly go back. This is something the book and oftentimes in a lot of chemistry classes gets glossed over. The source of the acid here. The most important thing is the acid that's used, the conjugate base shouldn't be a very good nucleophile. Otherwise, it's going to compete with the nucleophile you're trying to get to add in, right? So the acid that's usually used is sulfuric acid or phosphoric acid. And why are the conjugate bases for these acids not very good nucleophiles? Resonance, right? The negative charge is shared across a huge number of atoms, which means their conjugate base isn't going to really participate in a nucleophilic attack. The other one that you might see is Toslink acid. This is an organic acid. And just really quickly, let's take a look at what Toslink acid looks like. It looks a lot like tosyl chloride, right? But instead of a chlorine, we just have an OH. Same idea though. This proton on the top right here, if you pluck that off, that negative charge is now shared across 3 different oxygens through resonance, right? So it's going to be a really crummy nucleophile. So these are most commonly the acids that are used for these reactions. So be aware if you see them, they're just a source of protons, but not going to participate beyond donating protons. Make sense? All right. Let's do a practice problem really quick, and then we'll call it good. All right, for this one, first step is MCPBA. Second step is going to be Toslink Acid and methanol. I want us to determine what product or products we would get out from this reaction, and if it helps, try to draw all the intermediates as well. Now we'll give you a hint too. If you want to abbreviate things, what can we abbreviate that as? pH. All right, I'll get us started with the intermediate here, meaning the epoxide intermediate after step 1. Like I normally do, I just start out with an epoxide ring, and I tag on dashes and wedges onto each side, and then kind of fill them in as needed, right? So on that left-hand carbon of the alkene, we've got a phenyl group and a methyl group. It doesn't really matter which position we put them on, right? So I'll just pick one or the other. And then the phenyl group is on the same side of the alkene as this hydrogen, which means we should have a hydrogen there. And then on the back side, we should have a methyl group on the same side as the other methyl group. Do we have to worry about enantiomers here? Yes, absolutely. So this would be plus En. And then in the next step, we've got Toslink Acid, which is a good source of acid, or of protons. Toslink acid is a good source of acid. It's a good source of protons, so we can protonate the epoxide. Give us our protonated intermediate. All right. However, we still have methanol floating around. Which carbon is going to be attacked? The left carbon of the epoxide or the right carbon? Left one, absolutely. It's more substituted and it's tertiary in this case, which is the key important feature. Then the phenyl group is going to get flipped up like this. The methyl group will be flipped up like that. The other carbon was kind of untouched during this whole process. We're going to still have to worry about a mixture of enantiomers during this whole process. And what do you think the last step's going to be? Deprotonation. Did you have a question?
Yeah, so what happens if they're both tertiary substituted? Do we go by like the size?
Yeah, so if they're both tertiary carbons in your epoxide, you're going to end up with a mixture of products, most likely. In this case, the phenyl group provides a lot of stabilization, and why is that? Because of resonance, right? So in this case, if we had a tertiary with resonance versus a regular tertiary, the tertiary with resonance would win. All right, so last step is going to be deprotonation. That means that the Toslink acid that we used here really only needs to be catalytic, right? Because eventually we are going to need to deprotonate it later on. So I know we don't have class tomorrow, but I would really, really encourage all of you to use tomorrow to try to get ahead on sapling and do as many book problems as possible. Oftentimes these look really easy, but they get complicated pretty quickly, especially when we start jumping into synthesis. So if you can, even start reading ahead in the book and trying to do some of the synthesis practice problems. When we come back next week, we'll start doing more synthesis problems in class. Yep. That's a good question. So the question was, will there be a review session? Unfortunately not. I've got meetings stacked up on Friday. However, I'll be around tomorrow. So if you have any questions, you can stop by tomorrow. I'll try to send out an email too.